All right, Brian here, back with another Leetcode problem. Today we are doing Leetcode number 13, Roman to integer. This is a Leetcode easy problem, and you will probably get it if you are in a new grad or intern level role in a technical interview screen. It's not too bad. What we're going to focus on though is how to build the intuition to tackle this type of problem before we go into some live coding, and then we're going to cover the runtime analysis of the problem and how you should explain it during an interview. We're about to dive in the problem, but if you found it helpful by the end of the video and my explanation helped you understand the problem, please consider giving the video a like and subscribe. And without further ado, let's get into the analysis. All right, so let's read over the problem description together. We have Roman numerals are represented by 7 different symbols: I, V, X, L, C, D, and M. This is the Roman counting system. This is very standard. This is based in history, but the problem is nice and gave us this table of the conversions that we'll be doing. So for example, 2 as we know it is written as 2 in the Roman numeral with just 1's added. It goes on to explain the Roman numeral system if you're not familiar with it, which is that X means 10 and 2 is added to the end of it, which means this number is essentially X plus 2, which is 12. The number 27 is then explained, so on and so forth. However, it does explain some caveats to the system in which you have to remember that IV is 4, not 5, with the 1 before it. And it explains some more of these abstractions here. So if you need some time on understanding the Roman numeral system, I recommend you pause the video and watch how this works. Otherwise, I'm going to dive into the more technical aspects that are unique to this coding question. So scrolling down more, we see some examples. So if we have the string of III given n, we convert that to 3, IV 4, XI 9, everything that we would expect to see. And it gets more complex all the way up to what may be someone's birth date, MCM XCIV being 1994. So looking at this problem, we know that we have to do some type of string manipulation to it. And we also know that we're going to have a bit of a weird case in which, as we parse this through, we can't just go straight up left to right. We can't just say, oh, that's 1,000, 900, 1,000, and so on, right? It's not going to work out. We're going to get some bizarre number that looks nothing like 1994. And looking at the constraints, there's nothing giving too big of a hint here other than that our size of the problem is generally pretty small, even though it should be able to work up to an infinitely large size. And we don't have any true runtime constraint, though we're still going to solve the problem in an efficient manner. Thus, we have to go back up to the problem statement to build a bit more intuition of what we need to do for this problem, aside from our string manipulation. Well, we see that it writes out a bit of the caveats as the number 4 is written as IV because the 1 is before the 5 we subtract, making it 4. When we see the word subtract, that does give us a hint that we might have to do some subtraction in this problem, and otherwise everything else we'll be doing is addition to get to the number that we're summing up to. And similar to normal addition and some addition problems that I've done on this channel before, when we are adding something in code, we're not going to start from the biggest digit like the thousands in the example. We're actually going to flip it so that we start from the least significant digit, potentially being the ones place, and we're going to work our way towards the largest and most significant digit. So that's something that we need to keep in mind when we work with addition, even in the Roman system in code. So looking at the code here, we are working with Python 3 today as usual. And I know that we're going to need to keep track of an integer that we're returning. That's essentially our sum after all of the additions and subtractions. And we are going to keep track of the previous thing that we last, and we are going to keep track of what we last saw. So we know that are we adding or subtracting? And let me explain what I mean by that. We know that if we have xi, that means that 10, 1 is 11. As we see ix in a left to right system, that I is smaller than the x on its own. So we know that that I is probably combined with the x, which results in that actually being 9. And these hints all come from this paragraph here that I've highlighted. Based off of this, we know that we are going to write, I'm just going to write integer because we're doing both additions and subtractions, so it's not just a sum. And I'm going to write previous to keep track of what we have last seen, to know are we adding it just naturally? Are we going to have to keep track of this is possibly a prefix I, thus we have a ix or an iv or something like that. And not just that, we also have to keep track for x because x can be placed before L and C, and C can be placed before D and M. So it's not just one edge case that we can code in. We have to make sure that our code actually just naturally accounts for the fact that you can subtract prefixes to form a number slightly smaller. In this case, 4 and 9, 40 and 90, and 400, 900 builds us a pattern to work off of. So we're going to initialize these first to be 0, 0 with simultaneous assignment that we can do in Python to keep the code looking clean. And we are going to have to keep track of this conversions chart. Now, luckily they have written it out for us here, so we don't actually have to know this in an interview setting. And I'm just going to write conversions is equal to this table, which I already have copied in my clipboard. So with this conversions written out as a dictionary in which our key is our letters, the Roman alpha strings, and our values to each key is our numbers as an integer in Python. We can now do math off of these and some conversions with this table represented as a dictionary. And our dictionary lookup time is O of 1, which is constant runtime. So it's going to be super efficient as we go through this process. Now, recall earlier that I said that when we're doing math, like addition in this very traditional form, in Python, we want to actually look at this number as IIVXX because we're working from the least to the most significant digit. So we're going to have to reverse the string that we're given in actually. And the efficient and easy way to do that in Python is by using the reversed function, which has a linear runtime. So rather than writing that yourself, we're in Python, we can take advantage of the language's features. And one of those things we can do is instead of a for I in S, which is our string, and enumerating over every character of the string, we can call reversed. So what that will do is it will enumerate over every reverse character of the string. So instead of saying XXVII, we're going to have IIVXX. And then our for I will give us this first character as we proceed through and so on. So with that written, let's go down to the next line to write. We talked about earlier this case of adding and subtracting. So I think naturally we need to determine when do we add and when do we subtract from this number that we're returning. Well, let's look at this pattern here. If I comes before X as read left to right, we see that the smaller number comes before the larger number and it ends up becoming a 9 and it's read as that combination rather than being two disjoint numbers. Well, if it's read as a xi, we're just simply summing x and we're summing I naturally. So even though those two are kind of together or they could be disjoint, it doesn't really matter. Like now that we add the I on after that, it's 10 plus 1 plus 1, that's still 12. And that is different from how this works because if we have IIX, that breaks the pattern of x can be placed before v and x, and thus it will be a different case. So let's start by writing that out in code. Well, we know that if the current thing that we're on is a character, we can't perform math off of that or a comparison. So instead, we'll need to look at our table and convert our current element to a number. So that's the first thing. Make sure you don't forget that because otherwise we're going to be checking like if I is greater than v and Python's going to freak out. So we have if conversions I, which could be something like I is now 1. So if 1 is greater than or equal to the previous thing that we've seen. And the previous thing that we've seen right now is 0, but that's fine because we're looking at the least significant digit, so that's all good. So this will give us the first check. And then naturally, if something is not greater than or equal to it, it's less than it. So we can just simply write else, and then we can write do something here. So now tackling this case. If what we're currently looking at is bigger than previous, do we want to add it or do we want to subtract it? Well, working through this, if we reverse our array, we see I, and then we go on and see the next I, that is greater than or equal to what we last saw, which was also a value of 1. So 1 is greater than or equal to 1. And in that case, we want to sum them, right? Because 1 plus 1 is what we want to do. Likewise, as we iterate towards v, we're going to have 1 plus 1 plus 5. 10 is still bigger than the 5 that we saw before. So now this ends up expanded out, basically being 1 plus 1 plus 5 plus 10 plus 10. And that's totally fine. We don't even have to worry that XX and II are grouped together. So let's write that out. We initialize integer to be what we will be returning at the end. And we know that we want to add the current numerical value of what we're looking at in our for loop. So we can just write conversions I like we did up here. And we are just simply adding that to our integer as a running sum. And we know that we have to return that integer at the end. So we can just write return integer here. All right, that's not so bad. And now that we've done this advancement, we know that we have seen something already. So we also want to update previous, which we initialized here. So let's do that since that's not too bad. We have previous equals to conversions I because that's the last thing that we've already looked at and accessed. So now we need to figure out this minus case. How do we handle that weird trickiness? Well, it's actually not too bad. Like we did here where we just added two conversions, we're handling it character by character. So whatever we did adding something such as the x to make that number bigger, thus essentially say we're looking at this and we've summed now to 12 in xii. If there was an I before it, hypothetically, we would just want to subtract 1 from that, right, to make it 9. Granted, this is not how you would express a number, but that doesn't matter to the compiler. So we can actually just write integer minus equals whatever this conversions is. And we need to stop and think about that for a moment. If we look at our larger example here, say that we are looking at one where we actually do some adding and subtracting. If we start with v, we are going to toss that in here. We see that 5 is bigger than 0, and we're going to add that to our integers. Now we go to the next part of the loop and see that I is smaller than v, so we're going to subtract 1 from 5, and then our integer is currently going to have a value of 4. As we move on, we see that c is 100, given by our table there, and 100 is bigger than whatever we saw before, so we're going to add that. So right now we are at 104 in the sum. As we go further, we see that x is going to be 10. So we subtract that from 104, and that's actually now 94. And you can keep doing this pattern yourself, but what we've essentially shown is that even though we're processing it one by one, the number's starting to become the number that it should be, which is 94, because we end in 1994. So even though we shot out of bounds initially, it's totally fine where we're at now because we reached the number that we want to, and that's locked in. So with that example walkthrough, we can actually just try submitting the code now because it's looking pretty good and it matches everything that our example asked for. And bam, we see that it indeed does run with some flexibility. I've gotten it to run faster, I've gotten it to run slower. I've tried tweaking a few things, but ultimately this is a very clean and fast solution, and it's super simple. If you were asked to do this on an interview, you could very easily reason yourself through what am I missing and what do I need to build as cases based off of this paragraph given to me. All right, now with all that said and done, there will reach a point where the interviewer will say that they're happy with the code and they want to ask you about the runtime complexity or the runtime analysis of the problem, and they want you to say what the algorithm runs in and possibly asymptotic complex. And what they're asking for is that O of n that you might have seen before, where you can see it written in a comment as O of n like that. So let's do that. Let's explain it to the interviewer. So let's go line by line. In this first line, this has a runtime of nothing because assigning variables is constant. And this only has memory complexity of building a dictionary to n size entries. This does not use runtime, but this uses spacetime. So its runtime is constant, but its spacetime is O of n. Now in this for loop, there's something a little bit trickier going on here. Because I have added s here on its own line, this s is actually doing a conversion under the hood that takes O of n runtime complexity, and it's temporarily storing it that we can access as O of n spacetime. So that's O of n runtime and spacetime from that reverse loop. And then for I naturally is a linear runtime because we're iterating over every element of this string as a character. So that's O of n runtime plus this O of n runtime and spacetime. And if the interviewer now asks you what you're currently at, you are at O of n plus n, which is O of 2n. You are not at O of n squared. To get O of n squared, you would have had to have written another for I loop underneath this. So don't forget that. This reverse could be viewed as being written on the line before it. It is not nested underneath it. So our runtime is currently O to n, O of n plus n, and our spacetime is currently O of n plus O of n, so also O to n. Now, if we go through here, we're accessing in a hash map, we're summing to a variable, we're doing a check, we're accessing our hash map, we're summing to a variable, and likewise. So nothing here has any impact. This is all just constant operations in code. Of course, it does add very minimal, but it's not going to scale with the difficulty of the problem. So say that our string got longer and longer, these operations themselves aren't scaling and making the problem take longer to solve. Only this for loop is growing. So at the end of the problem, what I have said written out would look something like we have O of 2n because we have O of n plus an O of n runtime going on. Thus, the overall runtime can now be simplified because of how the laws of asymptotics work. Our problem runs in O of n runtime and O of n spacetime. And with that, our problem looks good. I'm happy with how clean it is, and you would be able to reproduce this code if you were in an entry level or intern level interview. Nothing needs to be fancier. You don't have to reverse this manually. This is what I would expect a interviewee to give me. All right, so now we have solved together number 13, Roman to integer, an easy Leetcode problem. And if this video is helpful, don't forget to give a like and subscribe to the channel. Drop a comment saying what Leetcode you want me to solve next. And thank you all so much for watching. Have a good one.